Okay, so welcome everyone. It's my great pleasure to have Professor Michael Kwok-Po today. Professor obtained his PhD from the Chinese University of Hong Kong in 1995 and is currently a chair professor in the Department of Mathematics, University of Hong Kong. Professor is a leading expert in scientific computing, data and imaging sciences, artificial intelligence, and machine learning, with foundational contribution to the algorithm for structural linear systems and image processing. He has published over 200 papers and several monographs, and he has been awarded the prestigious Foncom Prize and named as a Simon Fellow in 2017. He is currently serving on the editorial board of several journals, including Software Impacts, Journal of Scientific Computing, SIME Journal on Imaging Sciences. So today he will talk about the low-rank tensor completion with Poisson observation. So now the stage is yours. Thanks very much.
Yeah, thank you, Xu. Yeah, thank you very much for the invitation so that I have a chance to share my results. So today I'm going to talk about the low-rank tensor competition with the Poisson observations. So this is a joint work with Dr. Zhang Songchun from Central China Normal University. So you see in the title there are two keywords. One is the low-rank tensor competition, another is the Poisson observations. Maybe let's start with take some points or what is the basically Poisson observations and why we are interested in it. Because mainly with Poisson observation is one way to, what you can say, the model of the number of photons recorded in the absorbed image and videos. So usually the light sources emit the photons. So in that we can model and assume that these photons follow a Poisson distribution. So you can say that it depends on the properties of the light source. For Poisson distribution, there are possible. Free statistical distribution can be obtained for Poisson distribution. Depends on the variance and also the average number of the photon counts. So that can be Poisson 1, super Poisson, and a Poisson distribution. So this free statistics actually is comes across in the physics. For example, for the standard electromagnetic wave, that means the light sources. Usually we model as a Poisson statistics. But sometimes when you deal with some, say, for example, the quantum dot or quantum physics, that sub-Poisson statistics can be considered, like in the laser cases. For the super Poisson statistics, maybe when we're talking about the thermal, the light source, something like that. So, but of course, in the today talk, I'm focused on the Poisson distribution. And in the model, actually, the Poisson observation model is, of course, we do not go into the detail about in the acquisition of these photons, but we assume that we have some observed data that in this Y, and that comes from a Poisson distribution. And the underlying is actually the sources of the generate the Poisson distribution. That means the photon counts, and then the C is somehow the fixed background of the light sources, something like that. So we look at this model, and you see that with there are three indices, I, J, K here, that refer to what kind of the data we are doing the acquisition. So here is we can argue that this is a three-dimensional. So this is why we are interested in the tensor case. And X here is like the unknown tensor, which we aim to recover. So if you're familiar with the image, you know that if the order of the tensor is 2, then that means the tensor will reduce to a matrices, where the order of the tensor is referred to the number of the dimensions. So in this case, in particular in my talk, that I focus on the third order tensor. That means we acquisite observe the data like in a cube or something like that. So you have the three indices, I from 1 up to N1, J from 1 up to N2, and K from 1 up to N3. So for images, you can imagine this, the first two dimensions, actually, I and J refer to the spatial dimensions. So like you have the horizontal and vertical dimension of the image. And for K, that is we acquisite the data that would, the third mode refers to the time or frequency that commonly appear in the video or the hyperspectral data or the multispectral data. So the problem, of course, is now we have these observed data yijk at some points. So we mark it on the this set on omega. Then how we can recover the xijk? So this is unknown. Visually, what exactly the meaning now? I give you an example. So the left-hand side is actually a multispectral image, and the right-hand side is this is a video. So you see that here is we only observe some of the pixels because of the these lighting, the acquisition lighting system setting, or some reason we have some missing value. That means here is we only observe some of the IJK index. Okay, and then we want to recover the underlying, the so-called the tensor image, and this is what is referred to the mean of the Poisson distribution, and this is based on the Poisson distribution. How many you can model as how many photons we observed over a pixel that the photons count in average, something like that. So we want to recover like this. So this is the observed data, and this is somehow go through the processing. We get this kind of recover the data, and of course, if you zoom it like this one, at least you can see some of the window or the other. Okay, and the right hand side, this is a video. Okay, so you see that this is a light, under the lighting, a corridor of a video. Some people are walking along the corridor, and then you see that this is observed data. But based on this video, the third mode is talking about time, and the first and the second mode refer to these spatial dimension of the image. We want to recover this kind of the video in this case. Okay, so we mentioned that we consider this is a light follow the Poisson distribution. The next one is we have another because this is not a standard image. We observe the data in multiple frequencies or even related to time. So this is described as a tensor. So now the question is, what is the tensor? How we do the tensor recovery? So this is always a very, very interesting problem, and that is also in the last 10 years. I think a lot of the different research have been done along this direction. So visually, you can see that this is a one-dimensional tensor, this is vector, and two-dimensional tensor is a matrix, and cube is a three-dimensional tensor. This exactly we want to recover. Okay, but you can imagine if you have the 4-dimension, 5-dimension, or 6-dimension, or even high order, then if you visually you can put all the cubes together, and then this is a square of the cubes, and this is a cube of the cube. Of course, you can write more complicated structure. So in some sense, that is you see that is we keep some of the ordering of this spatial dimension or the time dimension or the frequency dimension, especially in the cube. And then we want to, based on this observation and their ordering, can we capture the underlying the so-called imaging data. There are, well, like the standard images, there can be a lot of different kind of interesting application. Just here is I give you some example for tensor. Like we want to do the background and foreground separation in the video, and color denoising. Color picture is actually you can say the simplest the third order tensor, because for the third mode you only have a red, green, blue dimension only. And then of course you can have a more complicated situation. You have a hyperspectral data, okay, and then this is a spatial dimension. So this third mode will be talking about different frequencies. In particular, for hyperspectral data, there's a lot of interesting application. We want to recover the unknown pixels. For example, if the sensor of the hyperspectral images there's some problem, or then we observe from the sky to the ground that is missing a lot of the regular pattern of data. So you want to fill in that what are their possible values, and also when we want to remove the cloud from your hyperspectral data, that is also quite common in the practical applications. So you see that there's some cloud here because we have other channel band that may be properly, or because of the other time instant, we observe these kind of data so that we can fill in back of the value, so that you can have a more complete pictures, so that you can do further image analysis or other purpose application. So you see that mainly is now we want to fill in back the values. So on the images. Now the question is how definitely that can be, it's a very ill-posed problem because you are missing some value. How you fill in? So of course you need to have some prior or some idea what is the underlying picture or they behave or what they are. So one of the very useful, you can say the concept or the characteristic used in imaging is we look for the low dimensional structure in images. So I think this kind of concept, low dimensional structure, is appear in many different kind of different data in data science, not just in images. But of course, how to describe this low dimensional structure is the key problem in the different data domain. In images, we can look for the repeated patterns, redundant sampling, or the other. This is for image standard. So you will ask how to represent this low dimensional structure is because this is just the two-dimensional image. Then that means this is mathematically, this is just a matrix. For matrix, when we know that SVD, the singular value decomposition, is a very powerful tool to describe or to understand the matrices itself. That means to understand the image itself. We can have these singular values and also the singular vectors. Then if you have the single, you can identify important singular vectors and also the largest large singular values. Then that hopefully will help you to understand the image, the property and the nature. And actually, the low rank of the matrix or the low rank of the for this image can be categorized by these how many number of singular values. So for image, we can do that. So for tensor, now, if you remember at the beginning, we say that we keep the ordering of these acquisition data. So for example, if you have the image, we keep the spatial dimension and also the red, green, blue, at least along this direction, the red, green, blue. Then the pixel wise and also the correlation between the red, green, blue, according to from the smallest frequency to highest frequency, for example. Then we base on keep this structure of the pixel, because we think that before we do any processing, if we keep it, that will be we can preserve some inherent structure and correlation. Of course, after the processing by some tools, the ordering will be changed. But why we need to change the ordering? Because we want to represent this kind of tensor into a low dimensional structure. Okay, so that means our hope is at the beginning we keep this structure, but after processing, okay, by some tools, you want to represent your tensor objects with a low dimensional structure. Okay, the same for time. You have the video, this time dimension, we keep this, but of course we will process it, because you know that if you keep this, definitely you cannot see so-called low rank structure or low rank representation in this tensor. So the question is how to represent the low rank structure inside. And this is we can formulate mathematical problem for how to minimize the rankness, because we assume the underlying is a low rank structure, because like the images, we expect that they have some low rank structure. Okay, so we based on this pi information, we want to recover the underlying the tensor objects subject to observation and the noise nature and etc. So now the question is how to represent the low dimensional structure. So for tensor, this is why this is I think in the past 10 years or even more is very interesting is how to decompose, to do the decomposition of tensor, because that in some ways to reflect how you represent the low dimensional structure of a tensor. So if you remember for a matrix, we can write a so-called rank 1 matrix, that's like the SVD, okay? Then you can do this decomposition. So that is very powerful and very useful. So for tensor, like in our objects, that we have IJK, then the question is very natural. We extend one more dimension. Okay, for example, we have A1, B1, then we extend one more. So this is like the CP. This is exactly called the CP decomposition, such that we can write the so-called rank 1 tensor, the decomposition of the original tensor. Okay. Another very common the decomposition is based on the matrix SVD. That means we have this third dimensional the tensor. Then we try to represent it in a compressed manner. That means this is very big. Then we say that can we have some compressed version of this X? So represented by this you can say the smaller one, so smaller g, and then now, of course, we go through some of the transformation or some of the representation of these entries. Okay, so you have U1, U2, U3. And why I say that this is computed through the matrix SVD, because the idea is because there are 3 directions or 3 modes. Each mode you do the unfolding from a tensor to a matrix, then you apply the matrix SVD, you will get the suitable U1 and another direction U2, another direction U3. And then after that, you combine together, that will be the targeting position of a tensor. So computational is very, very attractive because even for tensor, you can design your algorithm based on the matrix SVD. But for the CP decomposition, that would be difficult. We know that in general, that is NP complete. If I give you a three-way tensor, there's how to find out the sum of the random tensor decomposition. In general, this is the NP hard problem, so it's quite difficult to compute it. Okay. So these two are the study for a long time and very lateral extension of the matrix SVD. So now, recently, or also talking about about 10 years ago, the people also, Kumar and her research team members developed this kind of the tensor SVD. So again, is to try to decompose this tensor into another way. So the main idea is using the convolution. That means in here is a follow standard this matrix tensor multiplication or the standard multiplication of the entries, etc. But in this tensor SVD, the structure is no. We try to do this the convolution of the tensor. Okay, so you have a U star S star V. So that means in order to decompose this X. So the interesting thing here is the first, this is the convolution. Convolution means here is if you using the FFT or just like calculate the two sequence, the setting of the vectors. I think I have an example here. So the convolution, if you have a signal xt and you have another signal ht, then you can do the convolution of h and x together so that you can get the final value. So in some sense, you can consider, if you're familiar with signal processing and image processing, that means H is the filter, X is the income signal. You're using H to filtering the X to get the convolution signal, the output. This is look like in this way. So in this case, if this is a step function, is a constant function, because your filter look like this, then you were doing a cumulative sum of the X from this side, go over from the left-hand side to right-hand side. So you will get the convolution output will be like the moving average of them based on the given filter. So here is somehow like they're using the convolution. That means here mainly along the third dimension. That means they do the convolution using this tube as a tube, because you look at this ij entry, then you have a set of numbers m. The dimension is m3. They form a tube, and then you formulate another tube here. They do the convolution. That's what I just described it. Then based on this convolution, they prove that this, no matter what are the third order tensor, you can write the form in the U star S star V. This is universal, okay? Is here the convolution means what I present, or you can use the FFT because this is a standard convolution base. And here the U is also very interesting. Is they keep on some orthogonal structure, and V is also have an orthogonal structure. And here the S is look like this one. You have a tube form, okay, in here. So if you think about M3 now is equal to 1, so we go back to the matrix case, then we have a U is a orthogonal matrix, and then this S will be a diagonal matrix. So you see that is have the diagonals here, and then you have the V is also another orthogonal matrix. So now in some sense is this kind of extension of the matrix SVD, but using the convolution to represent the X into this form. And now instead of a so-called singular values of a matrix, now you have a singular. You can say you have a tube. This is look like a singular value, but not a number. It's a tube to represent like the sum of the information about the X. So this is somehow is very, very powerful. Then in a sense, it's because it's easy to use because it's a convolution base. and that means you only need to use the FFT and also the basic, the SVD, you can get this kind of the decomposition. And also because you see that here, we have the tube, you just count how many number of these non-zero tubes, then you can define the so-called the tuple rank, okay? Something similar to the rank of a matrix, but now you deal with the tensor. So you just count how many number of non-zero singular tubes of this S, and this will be the tuple rank of A, the tensor. And this is also, because this involves the convolution, you can also change in another way, is to just doing the FFT along this third direction. After that, we get a transformed or this tensor based on the FFT. Then you calculate what is the rank of the individual slides. Okay, so you can also get this kind of decomposition. So in terms of calculation, this is also very powerful and useful. And I show you some picture. This is the hyperspectral data. Then you will see that is now these original images. Then you have seen that if you have only the first component of the U and V, then what you get is some approximation of the original image. And then you have 5, 10, 12, 20, and 40, and something like that. So you will get a better approximation. Something similar to the matrix SVD case. Actually, you can also prove that this is somehow, if you consider this Tensor SVD, this kind of the truncation will give you the optimals, somehow the optimal approximation based on the truncation of the U and S and V transport in the decomposition. So this is very similar to, or like the analog to the matrix case. So now the question is, well, of course, we can use a CP decomposition or Tucker decomposition that has been as a low-dimensional structure to solve this kind of problem. And this research has been done for many, I mean, in some papers. So of course, our interest now is to look at the can we using the tuple rank to consider this problem. So in particular, that instead of doing the convex realization, is instead of finding out the tuple rank to represent it, we need to do the realization is like the tuple Euclid norm to do this kind of the computation or the robust case or etc. So mathematically, you can see that if you assume some of so-called the tensor incoherence conditions, then what happens is you can prove some of the theorem. We say that if you observe these the tensor data uniformly and with some governed by some rate rho, and then you have some this observed entry is corrupted by some probability gamma, then we can say that if you solve this kind of the realization problem, you can find you can with a high probability that you can recover the underlying the low rank tensor, and this rank talking about is bounded by the n2 over log n squared something. So that means in some sense is that this kind of the robust tensor computation result, you can sure that you can get some correctness or the exact recovery, okay, in the probability sense. Okay, I show you some before we talk about the tensor the Poisson case. This is we solved on this tensor computation or robust case. So we have the rho and gamma is to control this observation rate and the corruption rate. Then you see that is the right represent this successfully recover the tensor up to some numerical tolerance. So of course, you see that when the rank is lower, then would be better, or in some sense, it's easier for you to exact recovery the underlying low rank tensor. Okay, but of course, if you have the higher rank or even lower observation rate, the problem become more difficult, and also when the corruption rate is high, it's also more difficult. That's reasonable because you observe more data and you have less corruption of the data. That in some sense is more easy for you to recover. But of course, the low rank is somehow the key element. So this show you some of the picture of the color image denoising, and I think this is an average result on the database. Okay. Okay. So now the question is, I mentioned that of course the result talking about is the these we can recover the low rank based on this Tensor SVD convolution base. But the key question is this depends on the transformation. Okay, the rank somehow, because why? Because I'll go back to our maybe here. You see that is a convolution base. That means how you get this decomposition will be based on this operation, okay, of the two trips together. Here is use a convolution base. That means we equivalently we using the FFT to do this kind of the convolution. So you are talking about the trips, and the trips is based on the FFT to get your so-called low rank data. And definitely that means how many number of non-zero trips or what are they? These numbers will be governed by this transformation or the convolution. That means in here that will be the discrete Fourier transform matrix, because that will be the transformation we are using. But you can imagine why only the discrete Fourier transform? That can be other transformation. So we can also generalize the concept to other transformation. That means you can imagine this is like we are doing the generalization of the convolution. Instead of using the discrete Fourier transform, you're using any other, say for example the unitary transformation, and then we can also derive this kind of result. That means that for third order tensor, you can always have this decomposition. Okay, the U as V conjugate transpose, and U and V are somehow the so-called unitary tensor with respect to this kind of the transformation product. Because now instead of using the convolution or the FFT to compute the trips the number, but now we're using this transformation. Okay, then the S will be also have the diagonal tensor. That means you have these diagonal trips. So the question is, what kind of transformation you should consider in order to get the low rank structure of A? Because I give you the this kind of tensor, okay? But what I can play around the different transformation and then make the corresponding the rank structure will be different. So definitely FFT is one of the case, but you can using other possible transformation. And of course,
okay. Sorry to interrupt. May I ask one question? So,
sure.
Yeah, sorry to interrupt. So give a tensor like how to compute this transformation based on the FFT. Could you describe a little bit more?
Give the data how to find the so-called best or optimal transformation.
Yeah, no, I mean give a tensor how to find out this convolution-based decomposition, the US and V.
You mean FFT? You mean FFT? Or this
using FFT.
So maybe I told it too fast. In principle, it's a convolution, but
okay.
Also doing in this way is you apply the FFT along this strip. Okay, along this strip that is in the third mode. Okay, after that you compute the SVD for each slice. Then automatically you will get the USV, but USV will be in the original domain. But if you consider FFT along the strips and then take the SVD on this inside, you are talking about in the frequency domain of this version. But equivalently, you will get US and V. So this is also
so it's doing slicing. It's doing it slice by slice and perform like
yes, but the main difference
on each slice.
The main difference is here is before we do the slice by slice SVD, we actually rearrange the entry by using the FFT. Okay. This is also I mentioned at the beginning is and here at the beginning we have the tensor data. We keep this structure because we want the neighborhood will be next to us and also along the frequency or time dimension. But definitely there's no low rank structure. You cannot figure it out. But because of this transformation, this is one way. Of course, the CP and also other targeting system, they find their other transformation to help you to process the data. But for this TSVD, Tensor SVD, the idea is saying that actually they apply the transformation along the third mode. We arrange the entries along the time, along the frequencies, such that you can, after we arrange, then in the so-called the lower frequency pan, we further you use the SVD. That means to further to see how their correlation in terms of the spatial dimension to get this kind of low rank structure. So this is, I think, the main idea behind the Tensor SVD. It's not just simply slice by slide on the original data, because if this is the case, that would be just like you look at the inch frame independently.
I see, I get it. Okay, thanks.
So okay, so because of this, we can extend it the idea to the idea to sorry, I go back to here, is you can generalize it to more generalized information. I mean, sorry, the transformation. So, but of course, how to find out the optimal, so-called the optimal transformation? This is still a very hard problem, because definitely that will be data dependent. Okay, for what kind of image data, what kind of the transformation, that I can get this no tuple structure of your data. Okay, so this still I think is still an open problem, but at least you can generalize it to other structure. I mean the other transformation to the generalization of the convolution, and you can still define this called the transformed tuple tensor rank, because now we go through different transformation, so we call it transformed tuple tensor rank. And actually, we just try a synthetic data, random data, something like that. Is we compare with very simple transformation, like the wavelet transform, the half wavelet, then compare with the Fourier transform. So actually, we find that is the half wavelet can behave better than the Fourier transform. Yeah. So this is you see that is this kind of the data. But of course, here you can imagine half wavelet is very powerful to represent the piecewise linear function, because it's a step function. So if your data is somehow is a piecewise linear along the time, along the frequency, that may be a very better representation. But this is the fixed basis. So you can see that we're using this as an example. We have the original images, observe the image. We're using the full eye basis to represent the tubes, and wavelet basis to represent the tubes, or another adaptive one to represent the tubes. Then you will have the different result. So here you find that these two are the fixed basis to represent. U is somehow more adaptive, data adaptive. So you see visually, it also can be better. So what is the choice here is we very simple idea. We just do the tensor unfolding again and try to find the so-called the best basis. Because now after you do the mode-free unfolding, you have the many columns. This means the tubes right in the this unfolding way is a line matrix, very long. But in this case, that means I try to find what is the best representation among these tubes. So we just go through the SVD and then to find out the singular vectors for this. So then in this case, we pick up this as the transformation. So we say that this is more data adaptive. So you, of course, mathematically, we cannot prove that this is always optimal. It's still an interesting question. But we feel that experimentally, this is very good. And one way to see that why this is good is we can plot a histogram of this value. Now, this is only talking about the transformed tuple rank, okay? But inside, actually, this contains like the singular values of each slice after transformation. So if you put all these values on the histogram, you will see that how they distribute them. Okay, so you have a full eye basis, a wavelet basis, and also our more data adaptive basis U. So you see that if we plot this histogram, because this is real data, you don't expect exactly low rank. But if you look at the range of the singular values, some are big, some are small. But if you see that if you're using U, somehow they are more small singular values, so-called the singular values, compared with Fourier and wavelet. So in that sense, is if you say whether after this using this adaptive basis, I can get a tensor that is the low rank structure is a closer, okay, is a closer to a low rank structure, because you can imagine these other are very small value. So that means if you're using this U as an adaptive basis to do the transformation, then you can get a closer to a smaller low rank structure. Remember, in general, the theorem we say that is if you have the smaller rank, that would be easier, or in some sense is that you have a higher probability you can recover the exactly low rank. So that means this transformed tuple rank actually depends on the transformation. If you chose it properly, okay, then the transformed tuple rank is small. then your recover these underlying so-called low-rank tensor can becomes easier job. Okay, at least with a high probability you can recover. Or you can imagine if you just do the identity, that means identity as a transformation without doing anything, you can still perform the line slide by slide. Of course, you will find that the rank can be very high. Okay, so this is what you expected. So for image data, this is another demonstration to see that if we cut the percentage of the so-called of these singular numbers, how small they are, we keep 70%, 80%, 90%, or 95%. So indeed, you can see that we observe that this is the index of bands. That means I may go back to here. That talking about the index of bands here, and then we count how many number of non-zero structure after cutting off this percentage. Then you see that actually most of them are very close to zero. Okay, you see that? Okay. Of course, depends on what is the cutting line, 70%, 80%, that will become larger and larger. And also you see that is we're using this Tensor SVD. If you're using FFT or DCT or even the data adaptive one, they behave differently. Especially when you're using TSVD on the data adaptive basis, that will perform somehow better. Okay, because that you will get a lower rank structure. You will see that this line, correct? Because up to say here is 10, that will be almost all are zero. But for the red line and the blue line, you find that they may even up to the line 40 something in order to get a so-called zero. Okay, so in that sense, this also reflect this data adaptive basis is somehow more useful and powerful to get the so-called low rank representation of your tensor, at least for the image data. This is hyperspectral data set. I think I have another graph to show you. This is for video that will also behave more or less the same one. Okay, so you see that. Okay, so the question is actually because of we observe that this tuple rank is useful. So actually we find that some of the entries in these singular tubes, and actually they are very, very close to zero, or even they are zero. So because of this, so we think that maybe we can using a more refined incoherence condition. That means this is the summation of all the singular tubes of the non-zero number, and this is called the multi-rank structure in this transformed tensor. Okay, and to set up this incoherence condition, because of this reason, you can, if this happen, then actually you can use the smaller samples. Is enough for you to reconstruct the underlying low-rank tensor. In principle, we can prove that it's only like the n-log n samples for a n-cube tensor is enough for you to recover exactly. Okay, so this is some more further observation. Because in the literature, some are using the CP rank or Tucker rank, or later we consider the tuple rank. Then that will be different requirement on the sample size in order to guarantee you can recover exactly the underlying so-called low-rank tensor. So in this case, we find that one of the best results is by the in this paper. This is by Yunming from Columbia. I think his result is talking about n to power 3/2. So this is quite, but this is very, in terms of the capacity, this is a very, very good result because you are talking about deal with the n cube of the data points. But if you have this multi-rank structure, we find that we can further enhance to the n-log n square sample. Okay, so we also did some numerical comparison to see if we fix the sample size in terms of the n-log n square and then multiply the constant to see if we have this number of sample points randomly to see what is the performance of the different algorithms in terms of PSNR. That means how good in terms of this L2 error and also the CPU time. So you see that for our case, we get a very good PSNR. Of course, in terms of time, I cannot say we are fast enough because we still involve SVD, and especially now we deal with a more generalized transformation compared with FFT. That will be FFT even faster. But in terms of the PSNR, we get a much better performance. GOG is what I mentioned in terms of the capacity. This in terms of the theoretical capacity is the n to power 3/2. So, but we find that in terms of CPU time, that takes a lot of time because in particular, they need to prepare a lot good enough initialization in order to guarantee you can recover exactly. So because of this, the CPU time can be very high. But in terms of performance, because even we get this time, the performance, somehow I cannot say always the best. Sometimes it's still good. I mean, say for example, this one is better than if you have enough sample size, then in this case, the PSNL performance is better than FFT, but still lower than our data objective one or even the DCT one. Okay. So there's some more comparison, and this is somehow the hyperspectral data for comparison. Okay, so now we go after some review or talking about some related result about the tensor computation. Then I come back to my my original the title is the tensor computation model with the Poisson observation. Actually, the idea is something similar. We also using this transformed tuberan to help us to. This is the TTNN. Transform the tuber nuclear norm to govern do a convex relaxation to govern this kind of the tensor computation in the model. The difference here is in the tensor computation or robust tensor computation, we only match with the given data or how to decompose the tensor into the given entry and the noise entry, etc. But because now we deal with the Poisson observation, and the y is generated from the Poisson distribution, so we can do it by the maximum a posterior estimate on this Poisson observation. We can get this kind of the objective function in the recovery, and then to use the TTNN, the transformed tubular nuclear norm, to govern our so-called low-rank representation of this tensor data. And one more thing is in our previous result, we don't add any non-negativity constraint, but here, because we directly deal with the Poisson observation, so in this case, we also consider the non-negativity constraint inside. So this is the model we consider, okay, because we focus on the Poisson observation. Then we can prove some of the result. We also assume that this is a binomial model, observe the data under this uniform probability model. M is the number of observations, and N1, N2, N3 is the size of the tensor of these Poisson observations that you want to recover based on it. And then if somehow we can prove the error band, that this is after we solve this model, then what is the error between the underlying tensor and the computed tensor in terms of this error band, this upper error band, then that will be a lot of constant or whatever. But the more important is about the sample size and also the observation. So we see that this we can recover. We can say that we have this error band with high probability. It is 1 minus C capital N1 plus N2. N1 and N2 refer to the dimension of the vertical dimension and also the horizontal dimension of the spatial images. And M is talking about the number of samples. In this case, we use you can see that it's about N squared log N the data. Okay, this is because we consider only the transformed tuberan model. Okay, here our tutor is the transformed tuberan of this underlying tensor. And then if this is the case, then the error band will be governed by this. With high probability, this is true. Okay, under this binomial uniforming model. In order to interpret it, I think if you want to compare with simply, you can say using the transformation is identity, or you just perform slide by slides of the film or film by films of these tensor data. Somehow we have a better error band in terms of the matrix-based method is larger about this square root of n3 times of that in the film I show you. So that means the matrix-based method is no dependent between the things. You just do it as, film by film. Okay. You can simplify it, because if this is a fixed for fixed beta and c, the upper one, actually you can write down why we say that is about the about n log n, some n log n cube data, something like. If you have the n square log n number of observations. And I should here give a remark: the sample size and the error band can be further improved if we using the transformed tensor, so-called the multi-RAM, because this can be, if your data actually you can using the multi-RAM instead of tuple-RAM, that can be, this band can be further improved. Just like I discussed with this tensor competition case. We can also establish some lower bound. That means no matter what arbitrary algorithm you return this, then you can prove that this kind of observation based on this. And if you want to be this kind of a low transform tuple-RAM structure, then you will the lower error bound will be this one. Okay, with this probability. Okay, something like that. So that, and you can see the difference between the upper bound and the lower bound is only governed by this with a logarithmic vector, and then multiplied by this cube of the NV. Okay, so so this is somehow you can see the gap between the lower bound and upper bound, and we can say that this condition usually holds because the transform tuple-RAM can be bounded by this, even greater than NV, but cannot be larger than N2 times NV because of this tuple-RAM transform tuple-RAM structure, because it's talking about N1 and N2, how many number of these non-zero singularities. And also this is a fixed probability. Of course, it's close to 1, but we can also make it to be approximate to 1 arbitrary, just like in the upper bound, 1 minus, and then depends on the 1 over the size of the dimension, something like that. So in that sense, that we can approximate 1 arbitrary close. Okay, in that sense. Okay, so this is somehow the theoretical side. In some sense, it tell you that how good of the method, and based on the lower bound or the upper bound of the algorithm, and based on this transformed tuple-RAM assumption inside the data. So we do some experiment. This is multi-spectral data that I think I showed it at the beginning of my talk. Then now this is observed data. We based on this Poisson simulation. Then we compare with this PML-SVD. This is a matrix-based method actually. That means we assume no dependence among all the films, and then we just do it as film by film, and then to see what are the results. So you somehow is you see it's not too bad, but you see it's a little bit noisy compared with the other result, especially our result. I think it's quite reasonable, because you just have like a single image data, and now you don't involve another. So you can base on this to see how to do the recovery. So that can be very noisy. But if you think about dependence on all the films and then do the processing together, somehow the average effect you can figure out. So in that sense, that would be like you have some denoising effect instead of keeping some the missing value. We are not so sure whether you could cover it. This is also why I think that if you allocate the data in the tensor form, then it is good to process all the data in the tensor manner instead of the slide by slide. Of course, maybe there are other architecture or computational issues, but that is very reasonable. You try to process all the data together because they are somehow highly dependent, and this can help you to refill or recover the pixel appropriately. Okay, this is like the other low-rank tensor computation method. I think DNE. And then this is our model, but using the FFT, DCT, and even the data adaptive one. So in terms of the visually, you see that we have some good recovery, and also in terms of the SNR or SSIM, we are better than the other method. So this is also another hyperspectral data. So we also see that is we try to recover from this picture to get this. So this is our result. So you see that we are much more clear, okay, compared with the other method. So we also try on the different sampling ratio, and then to see that red line is our recovery SNR. So we somehow is very, in terms of performance, is better than the other method. Of course, compared with the matrix space, that is quite reasonable. Okay, and this is a video data. So again, we have this. I also showed this picture at the beginning of my talk. So you see that actually this is the light fixed background because I fixed the camera, but there are two people that are at least two here is walking along the corridor. So I think important is whether you can recover these walking people. So in here, you see the matrix space method have some problem because they do it film by film. So there's some difficulty to help you to see what is the correlation between the two films. But if you look at our method, I cannot say we are 100% correct because we still have the SNR only 23.5. But at least you see some of the people are now at least in the video, okay, in the recovery from this observed data. So I think this is somehow reflect the good thing of the method. This is another one. So basically, you see that there's two people, but here you cannot see any you cannot see two people, and here there's one person, but you cannot see. But at least here you can see the shadow or the other. Okay, so not 100% correct because this is still very in general is still I think it's a difficult problem. In particular for this one, it's only 15% for this picture. That means you only capture 50% of the entries from this video and then to try to recover. So I think overall still is ongoing research how to improve it always. This is based on the real image, but we try to using the Poisson model to look at it and to see is how good of the picture to recover. So here we're using some other metric to evaluate the different kind of method. Of course, visually you see that this is a good recovery. In particular, there's some artifact in the zoom you can see it, okay, comparatively. But in terms of our Q metric or PIQA, the metric to look at the single value of the gradient matrix of the patch image, we find that the performance is much better, and visually we also find that the performance is better than these other computation method or another matrix-based method. Okay, so I think more or less I need to stop my talk, but I think transform to rank is only one of the possibility to obtain the low dimension structure. But in general, we still ask the question is for your data, how to find out the so-called low dimensional structure in your data. It's still, I think it's a very, very important problem because if you identify it, that will be definitely help you to do the recovery for different data science problem. So in here, we try to do the convolution from the beginning and then extend it to the general transformation. But actually, you can also construct the low-rank tensor from the data by many, many ways. So for example, using more generalized filmnet or dictionary approach, even other coupled transform, because in the now we only consider on the third mode and then apply the SVD. But can we do it better? For example, I do the SVD first and then do the couple the other transformation, and also maybe we can do some data augmentation to increase the sum of the low-rank structure, or even we can search the patch and then to make the similarity to such that we can get a more low-dimensional structure. So I think all these are the popular methods worked in the image science, how to get the so-called low-rank structure. So for tensor data, we can also apply this kind of idea to the tensor data in general. And I think I better stop it here. So thank you very much. I think I summarized it. I report some of the tensor computation results under the Poisson observation, and also the report the theoretical result about the error band. One of the important issues is how to construct the low-rank structure, especially for tensor data. And then, of course, you can, in order to improve the method, can we also add other constraints like the total variation? That is very low. It's a local way to apply it to help you to recover the edges, in particular, one of the important image features. But you can ask what are there any theoretical results about the TV and also the low-rank structure, and also maybe we can consider sparse vectors in tensor computation that we haven't considered at this moment. So some of my recent work is also you can find in the DBLP, this database. Thank you very much. I stop it here. Okay, thank you. Thank you, Sonia.
Okay, thanks for the very nice and wonderful talk. So now let's welcome questions from the audience. You may just unmute yourself and ask.